Welcome to our video for Equilibrium Law. I would direct you to our PowerPoints to take a look at the notes to see the derivation of the law, how it's related to kinetics. We're just going to look at the process as to how to build the law. So if you're only watching this video, you might not quite get everything here. So hopefully this will be following your PowerPoint notes. With the equilibrium law, we want to build that ratio of the products over the reactants. And we want to have that ratio to equal the equilibrium constant. So that's a K and then a lowercase c. And that's representing our equilibrium constant. So we want to include the compounds and elements that are products in the numerator and those that are reactants in the denominator. First things first is to look through for any solids or liquids. Those are not going to be included in the equilibrium law. The only components of the reaction that can be included are gases and aqueous substances. So here we have gas, 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 so we're good. And let's put our products in the numerator. And we're going to put our reactants in the denominator. And then we're going to use the coefficients as the exponents. So going through here, there's a 2 in front of the NOCl. So I'm going to put a 2 here as the exponent, and also on the nitrogen monoxide. So, and that's our equilibrium law for this reaction. We want to look here at the Kc value, and there's some things that we can say about this. So in this case here, we're looking at, if we were to sort of sketch out the scenario, we'd see that NOCl kind of going down over time, but then sort of evening out. So that's sort of your reactant. And then the nitrogen monoxide and the carbon dioxide gas, or the chlorine gas, would sort of be created and then sort of peter out, sort of even out. And so at equilibrium, we would see that there would be more products than there are reactants. And the way we know that is because the K value, the Kc value, is greater than 1. So when that is the case, we're going to have more products than reactants. So products are favored. In our second example, we have hydrogen gas reacting with iodine, solid iodine to form hydrogen iodide gas. So looking at our reaction, we want to include, I am not in my room, so now we got a visitor. Let's roll with it. So we want to include only the gases or aqueous. Yeah. Sorry. We only want to include the gases or aqueous components. We don't want to include the liquids or the solids. And so we're not going to be using the iodine in the equilibrium law. So we'll still put our products on top. For me, I choose to put the exponent like right away as I'm writing it. And then for the reactants, we're only going to include the H2. So when we look at the Kc value that they give us, we can see that the Kc value is actually less than 1, which if we were to sort of look at how this reaction might occur, we would see the hydrogen gas sort of going down over time. So this was our reactants going down as they're getting consumed. The hydrogen iodide would increase as that product is getting produced. But at equilibrium, there would be more reactants than products. So for me, I'd like to think about it as like in terms of the fraction, where is the big number? If this was the big number, let's say this was like 5/3. If we had that, we would not end up getting a K value that's less than 1. So we would probably need to have something like this, 5/30. And then that could, if we did 5 divided by 30, then we'd have a decimal number, and we would have a situation where the reactants are the big value and the products are the small value. In this one here, we could have a situation where it's maybe like 30/5, where there's a lot of products at equilibrium and significantly less reactants. So when the Kc value is greater than 1, it means that the big number's on top, and therefore at equilibrium the products are favored.